Hey everyone, welcome back to week 15. This week I finished sections 4.1 and 4.2 from the Boyd book. So this is really where the book finally starts talking about convex optimization problems specifically. Not just convex functions or sets in isolation. So a lot of the sort of heavy, mathematical structure and machinery we've been developing, becomes useful. So for me, all the math I learned is really starting to fall into place. For today, I'm going to focus on the big ideas and results, also keeping the geometry in mind too, because that's important. So let's do it. The general optimization problem the book sets up looks like this. X here is the optimization variable, f0 is the objective function, and the rest of the fi's from 1 to m are inequality constraint functions, and the hi's are equality constraints. So each of these inequalities here, f of I x is less than or equal to 0, carves out a region, the sublevel set where the function is non-positive. Each equality constraint carves out a surface. The feasible set is the intersection of all of these. Why is it the intersection? It's the intersection because all of these must be true for this to be a feasible solution. Okay, here's a diagram in two-dimensional space. That means that x has two components, x1 and x2. And then you have three constraints here, inequality constraints. f1 here, which is the blue line. You also have the red line, and you also have the green line. The solution must be less than these values here. So this defines the feasible set x. Now, strictly speaking, we also have two more constraints. Can you figure out what those are? Well, from the diagram, x must be positive. So the constraints is that x1 is greater than or equal to 0 and x2 is greater than or equal to 0 as well. So those are kind of implicit constraints. So really we have 5 constraints here. Now, the optimal value is the minimum value that f of 0x, or in other words, the objective function can take that satisfies the rest of the constraints. Okay, I also want to mention the definition of a locally optimum point, because the contrast with global optimality is the main idea of section 4.2. So a feasible point x is locally optimal if no feasible point within some ball, Euclidean sphere of radius r does no better. Okay, so it's saying that x is a locally optimum point if for some other values around x such that those values are within this region, this ball region, are these values are bigger than this value of x, then this value of x is the smallest in that local region. So it's the local minimum. Before we get into convex problems specifically, I want to highlight one useful transformation which I think is elegant, and I actually saw in my linear programming class, but I didn't realize what it was, which is the epigraph form of convex optimization problem. So you introduce a new scalar variable t, and instead of minimizing the objective function directly, f of 0x, you minimize t subject to f of 0x being at most t. So let's compare these two forms here. On the right, we have the epigraph form, and on the left, we have the standard form. And so you might be able to just look at it and convince yourself that they're equivalent. But I won't go into the proof, but it turns out that x, the solution x and t on the right-hand side is optimum here if and only if x is optimum in the original and t is equal to f of 0x. But for now, we can see that the objective of the epigraph form is linear. So the geometric picture of the epigraph form Hopefully, I should provide more intuition. So think of the xt space as x being on the horizontal axis here, and t being on the vertical axis. If you remember, the epigraph of f0 is a region at or above the curve of f0 here. Minimizing t over that region just means finding the lowest point on the epigraph, in this case here. So minimizing over the function and minimizing t over its epigraph are the same problem, just written differently. The payoff is that a linear objective is universal for convex optimization. We can always write the standard form in the epigraph form and find the linear objective function here. So far we've only been talking generally about optimization problems, which covers everything. But now let's talk specifically about convex optimization problems. So a convex optimization problem is the standard form, except now with 3 additional requirements. So we can see here that we have this same thing. We want to minimize the objective function according to these constraints here. The first difference is that f of 0, or the objective function, must be convex function. Also, the inequality constraints must also be convex. Lastly, the equality constraints must be affine. The reason that the equality constraints must be affine is because that if h of x equals 0, it's really saying h of x is less than or equal to 0 and negative h of x is less than or equal to 0. So in other words, h has to be both convex and concave, which forces it to be affine. So here's the key geometric consequence. The feasible set of a convex problem is always convex. Why? Because you're intersecting the domain, which is convex, the sublevel sets, and hyperplanes, which is here. And of course, the intersection of convex sets is still convex. I'm going to reuse the last example we used because we can see that the 3 constraints, inequality constraints, are also convex. They're just linear, right? So that forms a feasible set that's a convex set. So the whole problem reduces to minimize a convex function over a convex set. Geometrically, you can think of this as a bowl-shaped objective sitting over a convex region of its domain. Here's another diagram just to illustrate my point. We have the objective function here, which we want to minimize, and we have 2 variables x1, x2. So we can see here that the feasible set here is just illustrated as a circle. It sort of spreads out evenly, as you can see from this shape here. And the optimal value is the value of x, which minimizes this objective function. But notice the significance of what we just talked about. This bowl shape has to be convex, and the objective is also convex itself. So now I'm going to talk about locally optimum points being the same thing as globally optimum points, which is essentially the main theorem in convex optimization. So the claim is that in convex optimization problems, any locally optimum point is also globally optimum. So I'm going to walk you through the proof here. So suppose x is locally optimum feasible and no feasible point within a ball radius r does better. So suppose for contradiction that there's a feasible y such that f of 0y is less than f of 0x. Since y is better than x, it must be outside the local ball. In other words, the 2 norm of y minus x is greater than r, our radius. So geometrically, x is the local minimum in its neighborhood, y is somewhere far away that's lower. So in a non-convex landscape, this is totally possible. Think of this function as an example. We see here x is here what we're talking about, but the function evaluated at point y is better, and we can see here y is actually the global minimum as well. But now let's use convexity. So we construct a point z that's a convex combination of x and y. So here Z is the convex combination, and we define theta pretty cleverly with R over 2 norm of the difference between y and x. Now, by construction, the 2 norm of z minus x is equal to the radius divided by 2, right? Since the feasible set is convex, both x and y are feasible, and so z is feasible. And by convexity of f is 0, we have this inequality here on the left side. So z is feasible inside the ball and strictly better than x. But that contradicts our local optimality that we assumed in the first place. So no such y can exist, and x must be the global minimum. So this picture here, if we assume convexity, cannot exist. So really, the correct picture is something like this. We just have some point, the objective function evaluated at point y, evaluated at point x. As we take the convex combination, point z, and then evaluate at point z. So a convex function or a convex set has exactly one sort of valley, so to speak. There is no way to have a local minimum that isn't also the global minimum because the function can never dip down somewhere else. In the last part of the video, I'm going to talk about optimality conditions when the objective function f of 0 is differentiable. So we already know from chapter 3 of the first order characterization of convexity. Hopefully this inequality looks familiar. So it says the function always lies above its tangent hyperplane. Using this, you can show that x is optimal if and only if x is feasible, and this second expression is also true. At f of 0, evaluate at x makes a non-negative inner product with every direction, y minus x, into the feasible set. Equivalently, negative of the gradient of f of x of 0 points away from the feasible set. The negative gradient defines a supporting hyperplane to the feasible set of x. So you can't move into the feasible set and decrease the objective. So here's a diagram that illustrates my points. The optimum point x star sits on the boundary of the feasible region. The gradient of the objective function is pointing outward, sort of away from the feasible region. On the other hand, the negative gradient is obviously pointing in the other direction, toward the feasible region. And the supporting hyperplane right here at x star is a solid tangent line to the feasible region. Finally, we can see I've drawn some level curves here. So this is where the value of f of 0 is constant. So if there are no constraints to our problem, every direction is feasible. So the condition, the gradient of f of 0, x times y minus x is greater than 0 for all feasible y in our feasible region, is true for all directions, y minus x. So that just simplifies to the following condition. So all we need is the gradient to be 0. And we can see that from a simple diagram. The gradient here is 0, and that's of course our optimum point. Every direction is pointing upwards. Now, if you only have equality constraints, so if you remember those h of x, then the feasible set is an affine subspace. The feasible directions from x are exactly the null space directions v such that av is equal to 0, right? So here's our second optimality condition, only when we have equality constraints. So here, x can't vary in all directions. It can only vary exactly in the null space, this n of a here. So instead of the simple gradients being greater than or equal to 0, we have the gradient of f of 0 x transpose times v is greater than or equal to 0 for all v in the null space of a. But on the other hand, if a linear function is non-negative on a subspace, it has to be 0. So we have, they have to be perpendicular. So the last equation here is the Lagrangian multiplier condition. So we'll get back to this later, and we'll explore this more in depth in later sections. So here's the diagram to show what I mean. Notice that the feasible region is not really a region, it's just a line because we have equality constraints here, not inequality. And the optimum point is the x star here, like this. Now notice that the level curve of f of 0 is tangent to the point x star. So this is a geometric interpretation that the gradient is orthogonal to the feasible directions, in this case, the null space of A. Finally, for case 3, if the only constraint is x is greater than or equal to 0, the feasible set is the non-negative orthants, right? So working through this condition, the optimality conditions come out to. So this last condition here is called complementary. For each coordinate I, either x of 0 is equal to 0 or the ith partial derivative is equal to 0. So they can't be both equal to 0 at the same time. So what this means geometrically is if a variable is strictly positive, you're in the interior of the orthant in that direction, and the gradient must be 0 there. Otherwise, you can move along that coordinate to improve. If the gradient is strictly positive in some direction, the optimal x must be 0 in that coordinate, so you're against the boundary now. So what this is saying is that if the optimal value of the first component, x1, is greater than 0, then that implies that the first component of the partial derivative of the objective function is equal to 0, and vice versa. So we'll see complementary again in dual problems. So we'll study more if this doesn't make so much sense now. All right, so to recap, the standard form gives us the setup. The epigraph form shows that a linear objective is universal. Sort of the local is equates to the global minimum. It's the core theorem that makes convex optimization tractable. And we also saw the condition, which gives us that criterion, the first and second order conditions. So, honestly, for me, this week was the coolest week, over this past 15 weeks for me. Because, I've taken linear programming before, and I kind of knew all the math that, we've been doing will pay off later. And seeing it actually pay off and seeing that take place was just the coolest thing ever. So with that said, I'll see you next week.